Section 2.5 uses something we call sig figs. So our aim for this section is to learn to determine the number of sig figs in a calculated result. This means we need to be able to do addition, subtraction, multiplication, and division, and then to be able to figure out how many sig figs are in our answer. So we need to know what sig figs are first. There are several different rules when we're determining how many sig figs are in a certain measurement. So sig figs stands for significant figures or significant digits. Non-zero integers are significant. They are always significant. So that means any number that is not zero is always significant. For example, the number 1,457 is going to have 4 sig figs because it has 4 numbers that are not zero. The number 124 has 3 sig figs because it has 3 numbers that are not zero. Anytime you have an integer that is not zero, it will be significant. Significant just means it matters in your measurement. Then there are zeros, the types of sig figs that are zeros. And there are different classes of zeros because they can fall at different places in the number. The first is what's called a leading zero. So leading zeros come in front. They are never significant. So we put zeros sometimes in the front of a number like that in order to show that we do have a decimal. Those numbers are not actually part of the measurement. They are showing us where the measurement begins. So the number 0.0025 has 2 sig figs. The number 0111, even though we normally wouldn't write numbers in this way, but just to show you that that 0 in front does not matter. That number has 3 sig figs. The next class is captive zeros. So if you're captive, you're trapped. You're in the middle of 2 zeros or in between, or 2 non-zero numbers. You're in between them. These are always significant. Since they are trapped between 2 significant figures, they themselves are significant. So the number 108 has 3 sig figs. And then the third kind are trailing zeros. Trailing come at the end. They are behind everything else. They are significant only if there is a decimal point in the number. So the number 100 with no decimal point has only 1 sig fig because that's like us saying we can read the 1, but everything else we have to estimate. So we can't count those as significant digits. The number 100 with a decimal point tells us we were able to estimate to the number 100 with a decimal point. So that's 3 sig figs. And the number 10 with a decimal point tells us we could read the 10, but we had to estimate the 0. All of those numbers are part of the measurement. So that is 3 sig figs as well. So we have leading zeros, the zeros that come in front, captive zeros, the zeros that are trapped in the middle, and then trailing zeros. Each have their own rules. Exact numbers. So an exact number has an infinite number of sig figs. So what does this look like? Look at how many people are in your room right now. If you're by yourself, there's going to be 1 person in that room. You can't have half of a person. So I can't represent the number of people in a room as 0.5 or 1.5. I can only represent that number as 1.000000000000 and so on. The zeros go on to infinity because I can never have a decimal number there that would represent a fraction of a person. I always have to have an infinite number of zeros. And then, for example, anytime I have an equivalent statement, which means I'm talking about how one number is equal to another, I'm saying, for example, here that in 1 inch, I have exactly 2.54 centimeters, which means I can't have a 1 in this area right here, or this number can't be a 2. If that number is exact, it's considered to be followed by an infinite number of zeros. You do need to know this, by the way. This comes in handy. We use this quite often when we're going back and forth between different units. 1 inch equals exactly 2.54 centimeters. 2.54 followed by an infinite number of zeros. Any equivalent statement, and we will look at those in the coming sections, are considered exact numbers. So they have an infinite number of sig figs. So pause your video, do these practice problems. We will come back together and then I will show you how to solve them. We're asked here how many sig figs are in each of the following numbers. So looking at the number 0.00100, we're applying two different rules here. Remember, when we're looking at zeros, leading zeros don't count. So these two numbers are not significant. Any non-zero number does count. So 1 counts. And the rule with respect to trailing zeros says trailing zeros count as long as there's a decimal point in the number, which there is. So we end up with 3 sig figs for this number. And in the next one, we don't look at this part. All we care about is what's going on in what's called the mantissa of a number written in scientific notation. 2.0800 is what we care about. So we start from left to right, and we see that we have a non-zero integer. We then have a captive zero, another non-zero integer, and 2 trailing zeros. And that gives us a total of 5 sig figs. And in the last one, you might look at this and think that there are 2 sig figs. However, since we're talking about something whole that can't be divided and still maintain its integrity, so what I mean by that is I can't have half a beaker and still have it be a beaker. Therefore, I have an infinite number of sig figs in the number representing 480 beakers. The other thing we have to be aware of when we're dealing with sig figs is the correct way to round. There are different methods out there, but we use the method involving the number 5. So if the final number is less than 5, you're going to round down. So in this case, if I'm asking you to round to 2 sig figs, you would draw a line after 2 sig figs, and then you would look at the number that you're cutting off, which is right here. Now, that number is lower than 5, so that means the number just before you drew that line is the number that you're going to round. That number becomes 1.3. Now remember, this is if I'm rounding to 2 sig figs. Now, if the final number, or the number that I'm cutting off, is greater than or equal to 5, I'm going to round up. So again, I'm going to ask you to round this number to 2 sig figs. You draw your line in the same spot. This time the 8 is what you're cutting off. 8 is greater than 5, so that rounds the 3 up. So your final answer, rounded to 2 sig figs, is 1.4. Now we can apply these ideas to sig figs involving calculations. So there are 2 different rules, and it depends on if we're multiplying or dividing, or adding or subtracting. So we'll start with multiplying and dividing. In this case, we're looking at multiplying or dividing numbers, and we want to look at the smallest number of sig figs. So this is going to determine how many sig figs are in my answer. So for example, if I'm multiplying the numbers 4.56 and 1.4, the answer I get is 6.384. So what I want to do is look at the numbers that I'm multiplying and identify the number of sig figs in each of those numbers. So in the number 4.56, I have 3 sig figs. In the number 1.4, I have 2 sig figs. So how many sig figs are going to end up in my answer? 2, because 2 is less than 3. So what I want to do now is round that number according to where I need to cut it off. So 2 sig figs means I'm drawing the line after 6.3. 2 non-zero integers means those 2 numbers are significant. I want to cut everything after it off. So I'm only looking at the most immediate number. I don't care about that 4 at the end because it's after the 8. It is less significant than the 8 is. So I'm cutting off the 8 at the 8, and that 8 is greater than 5. Therefore, that rounds the 3 up. So my final answer is going to be 6.4. If I'm looking at addition or subtraction, this is a little bit different. You're looking at the number with the fewest decimal places to determine the number of sig figs in your answer. So for example, if I'm adding up the numbers 12.11 plus 1.013 plus 18.0, I want to look at the number that goes the least number of places past the decimal point to guide my answer. So what I want to do is line these up at the decimal point because I'm looking for the least significant number. So what I want to do here is go ahead and calculate the answer, and then you're just going to draw a line straight down the least significant number, which was this one right here. So I can see that that number only goes out to the 10th place. So I want to draw my line down through all of those numbers so my answer doesn't reflect any more certainty than the 10th place. So when I do that, I'm going to round again according to the number that I'm cutting off, which is a 2. 2 is less than 5. It's going to round that one down. Now don't round it down to the next digit because I'm not going all the way down to 31.0. I'm going to keep that right at 31.1. And this is a mistake a lot of people make. If they're starting at 31.12, which is what we see right here, they think they're cutting off the 2. They think that the 1 rounds down and they end up writing something like 31.0. But I don't want to do that. That's going too far. This tells me that it just brings this down to 31.1 because you can think of this as 12 is between 10 and 20. So you're not rounding all the way down to 0, you're just rounding down to what would be 10. So be careful of that error. Please take just a minute to pause your video, attempt these practice problems, and then come back and resume your video to see if you're correct. In this problem, we're asked to perform each calculation rounding to the appropriate number of sig figs. So performing the calculation itself is only part of what we have to do. The second part is to actually determine how to round our answer based on the number of sig figs in each of these problems. So the way we start is by performing the multiplication. And in this first one, if we take a calculator, you have a calculator on your phone, you can multiply 4.2 by 3.45 by 6.23. And what you get is 90.2727. So there are a lot of decimals in this answer. So we want to cut that down. We want to make it a little bit more concise. So we need to look back at our original numbers and we need to determine how many sig figs are in each of those numbers. Remember, the rule for multiplication is that you take the number with the least number of sig figs, and that is what guides your answer. So in the number 4.2, we had 2. The number 3.45 gave us 3, and the number 6.23 also gave us 3. Remember, according to the rules for sig figs, all of these numbers contain non-zero digits, so we're just counting the number of non-zero digits in each of these numbers. So how many sig figs will we end up in our answer The lowest number here is 2, so we need to round this number according to 2 sig figs. So we count over from the left to see what 2 sig figs looks like, and that number is 90. Now, if I'm just going off of this number, this is not 2 sig figs because remember, final or trailing zeros do not count as significant digits. I need to be sure I put a decimal point in that number to make the 9 and the 0 significant. So our final answer here is 90 with a decimal point. That decimal point is important. The next step, or the next problem, gives us subtraction. So the way we want to approach this is to remember to line everything up at the decimal point. So we have 8.23 minus 3.51 minus 2.645. So when we put this number in the calculator, 8.23 minus 3.51 minus 2.645, we get 2.075. And addition and subtraction work a little bit differently because the way you approach this is to go to the number that goes the least furthest past the decimal point. So lining these up, we can see that both 8.23 and 3.51 go 2 places past the decimal point. So that is where we're going to cut off our answer, right there. So we're not looking for a number of sig figs here. We're looking for the number of places past the decimal point, and this is only for addition and subtraction. So what we're going to do, we know we're cutting our number off at the 7, so we just want to see if that 7 rounds up or down. We're going to look immediately to the number that we're cutting off, and that number that we're cutting off is 5. Remember, numbers equal to or greater than 5 round up,
So this number becomes 2.08. So we're not concerned with how many sig figs are in this answer when we're applying it to addition and subtraction problems. We're concerned with where we're cutting it off past the decimal point. And then in the last one, we're looking at two different mathematical operations, but they fall into the same category because in both multiplication and division, you're looking at the number with the least number of sig figs. So if we put this in our calculator, 2.4 divided by 8.2 times 8.923, what we get is 2.61160976. And then we want to look at the least number of sig figs. So the number 2.4 has 2 sig figs, 8.2 also has 2, and 8.923 has 4. So both of the 2's will guide the number of sig figs in our answer. When we cut this off past 2 sig figs, we're cutting off the 1. 1 rounds the 6 down. Rather than saying it rounds it down, we can also say that it keeps it the same. So our answer for the third problem is 2.6. So we end up with 90 with a decimal point, 2.08 for number 2, and the number 2.6 for the third problem. An extension of this practice would be looking at how we can combine multiple operations within one problem. So for example, if I had a subtraction problem followed by a multiplication problem, all within the same operation, what I would have to do is use my order of operations. And you should know from a math class that we're looking at PEMDAS. That should sound a little bit familiar. If it doesn't, what that's referring to is parentheses, exponent, multiplication, division, addition, and subtraction from left to right. So you can also apply this in a multi-operational problem if I asked you to go one step further as an extension problem.